This lesson is on the fundamental theorem of calculus. Before you do this lesson, you should have had a lesson on definite integrals and have learned that a definite integral is found by taking the limit of an infinite sum. You're going to find that the fundamental theorem of calculus will really simplify the work that's required to evaluate a definite integral. The fundamental theorem of calculus says if a function f is continuous on the interval from a to b, then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f on the interval a, b. In other words, to get the value of this definite integral from a to b, all we have to do is find an antiderivative for our integrand function and then evaluate that antiderivative at the what we call the upper limit of integration first. Then notice you subtract and you put in the value of your antiderivative at the lower limit of integration. The important thing about this theorem is that we no longer have to do this limit of a sum. It says provided we can find an antiderivative, we can now calculate the value of a definite integral without having to find the limit of a sum. I'm sure you agree with me, having to do those upper rectangles or lower rectangles is really difficult sometimes. And then even after you get that thing set up, sometimes finding the limit of that infinite sum is really difficult. Now, I'm going to put the definition or the fundamental theorem of calculus back up here, and there's a couple of things I want to point out again. The first thing I want you to notice, it says our function f, that's your integrand function, must be continuous on our interval from a to b, and you'll notice a and b are our limits of integration. It's always real tempting when you start working these definite integrals using the fundamental theorem of calculus to overlook this idea that the function is continuous. So I have some examples where we're going to point that out. Again, I remind you, find an antiderivative and then you evaluate at the upper limit first, then subtract, and then you put in the lower limit. Now, we're going to look at a couple of examples and use this fundamental theorem of calculus. We want the definite integral from 1 to 3 of the function 2x cubed minus 4x squared plus 3x minus 5 with respect to x. This is a polynomial function which is continuous everywhere. So I'm not concerned about this function not being continuous between 1 and 3. Okay? So let's find an antiderivative. So this is sort of like you did when you had indefinite integrals. Just ignoring these numbers, we're going to look here and find an antiderivative. So since this is a sum and difference of functions, we can do this function first, and we will bring down our constant 2, and then on our power of x, we'll add 1 to our exponent, making it a 4, which will place a 1/4 in front. Then we'll bring down our minus 4. We will add 1, make this x cubed, which will put a 1/3 in front. Plus, we'll bring down the constant 3. Add 1 here, we get x squared with a 1/2 in front. And then minus, let me put it right here, 5x. Now remember on indefinite integrals how you always put a plus c on there? I'm going to go ahead and put a plus c, and then I'll show you why we don't really have to do that. Now, this is our antiderivative. According to the fundamental theorem, we want to evaluate this antiderivative over these two numbers. Now, before we evaluate, we're going to simplify a little bit. So what we usually do is at the end of our antiderivative, we put a straight line and we recopy these numbers, 1 down here and 3 here. This is just a reminder that we are going to evaluate this function. Now, let me simplify this just a little bit. 2 times 1/4 is 1/2, so we have 1/2 x to the 4th, and of course minus 4/3 x cubed plus 3/2 x squared minus 5x plus c. There's our antiderivative in a more simplified form. And again, I'm going to put that straight line there, reminding me to evaluate. Now recall that we put the upper limit of integration in first. So we're going to replace all of these x's with a 3. Okay, 3 to the 4th is 81. So I'm going to write this first term as 81 halves. Let me bring it down here so we'll have plenty of room. 81 halves. And then we'll put 3 here. 3 cubed is 27. 4/3 times 27. 3 would cancel with 27 and leave a 9 times that 4 makes 36. So that will be a minus 36. 3 squared is 9. 9 times 3 is 27. So I have 27 halves. 3 times that negative 5 makes a negative 15. And since this is just the constant c, we're just going to put that down. There's not a replacement there. So we have put in our upper limit of integration into our antiderivative. Now we subtract, and now we're going to evaluate this antiderivative at the lower limit. So we're going to replace all of these x's with 1s. That would give us a 1/2 minus 4/3 plus 3/2 minus 5 plus c. Now let's combine some of the things that we have. I have 81 halves plus 27 halves. I'm going to go ahead and write that as 108 halves. We'll simplify that in a second. Minus 36 minus 15 is a negative 51. I have plus c. Now 1/2 plus 3/2 is 4/2. Right? So I've got minus, I'm still going to use that parenthesis, 4/2. I'm just going to leave that negative 4/3 for right now. We'll come back and pick that up in a second. Minus 5 plus c. Now notice this negative is going to distribute here. So this will change to negative 4/2 plus 4/3 plus 5 and a minus c. And then we can change that to addition. Notice that your plus c here and your minus c here will cancel out. That would happen every time with these definite integrals. So because of that, we generally do not put a plus c on our antiderivative when we're doing a definite integral. Now don't forget, it is still necessary to be there on indefinite integrals. Now let's go ahead and finish simplifying. I'm going to put these halves together. 108 minus 4 gives me 104 halves. I have a negative 51, and a plus 5 would be a negative 46, and then I still have that plus 4/3 right there. Okay? Now 2 will divide into 104 evenly. It will go 52 times, so this fraction is 52, isn't it? 52 minus 46 gives me 6. 6 plus 4/3 is the same thing as 6 plus 1 1/3, so that's 7 1/3, or if you prefer to write it as an improper fraction, 22/3 for our value. Recall that a definite integral always gives you a numerical answer here. Alright, on our second example, we have our integrand is 7 times the square root of x. Now you'll notice you're integrating from 0 to 25. 0 to 25 would contain all positive numbers and the number 0. The square root is defined for all of those values, so this function is continuous there. I'm going to rewrite my integrand in the form of 7x to the 1/2 power. And then we will find our antiderivative. So we'll bring the 7 down. Adding 1 to our exponent, we have 3/2, which puts 2/3 in front. I'm not going to put the plus c on it this time. We're evaluating from 0 to 25. Well, again, let's simplify just a little bit. 7 times 2/3 is 14/3. And I want to remind you that x to the 3/2 means the square root of x cubed. I want to write it in that form so you can think about it as we evaluate. So we put the upper limit in first. We have 14 thirds times the square root of 25 cubed. And then we have minus 14 thirds. We'll put in the lower limit, square root 0 cubed. Of course, the square root of 0 is 0, and so we'll get 0 times this 14 thirds. That term will go away. Now here we have the square root of 25 is 5. 5 cubed is 125. So I have 14 thirds times 125. I'm just going to put that over 1 and multiply 14 times 125. That is 1,750 over 3. We know that fraction won't reduce, by the way, because 3 is not a factor of either 14 or 125. So what we're showing you here on these definite integrals now, it's much easier than what you had learned before. You simply find an antiderivative, simplify it down, then evaluate it. Put in the upper limit of integration, then subtract, put in the lower limit of integration. And I caution you, be careful when you're doing this subtraction. Always bracket this off so that you get all of your signs correct. Now, if you look at this next example, it says to evaluate the integral from 0 to 2 of 1 over x dx. What I see students doing a lot is they just kind of go along. They say, well, I know an antiderivative of 1 over x. That's the natural log of x. And I'm going to evaluate that from 0 to 2. And so they proceed to say the log of 2 minus the log of 0. And if they're not careful, if they don't recognize the log of 0 is undefined. Okay, so we have a problem here. What they didn't do is take the time to look at the integrand and ask, is this function continuous from 0 to 2 on the closed interval from 0 to 2? Well, you see we have a problem at 0. 1 over 0 is not defined, so my function is not continuous at 0. That means I cannot do this definite integral using this process. That was incorrect. Even though I can find an antiderivative, that process does not work. Look at the second one. I could certainly find an antiderivative for the square root of x minus 2. That would not be a problem. But I want you to notice your interval. If you substitute a 0 for x in here, is 0 minus 2 under a square root defined? It isn't, is it? In fact, for this square root to be valid, x minus 2 has to be greater than or equal 0, which says x has to be greater than or equal 2. And between 0 and 4, about half of that interval, from 0 to 4, half of that interval, our function is not defined there. So it is not continuous there. So again, we cannot do this definite integral using the fundamental theorem of calculus. All right, well, let's look at a couple of trig function definite integrals. Evaluate the integral from 0 to pi of 3 times sine x dx. Well, we can find an antiderivative, can't we? And by the way, the sine of x is continuous everywhere, isn't it? Okay? So we have no problem with continuity. We're going to bring our constant of 3 down. The antiderivative of sine is negative cosine x. We're evaluating from 0 to pi. So I'm going to draw that line and remind myself I'm doing that. Now I'm just going to rewrite this as negative 3 times the cosine of x before I substitute in. Alright, remember you put the upper limit in first. So I have negative 3 times the cosine of pi. Then you subtract. Be careful with your sign, so I'm going to use a parenthesis. We're going to put 0 in. So negative 3 times the cosine of 0. Alright, well, let's evaluate. The cosine of pi is negative 1. So I have negative 3 times negative 1. These signs are going to change, aren't they, to plus. Plus 3 times the cosine of 0. Well, the cosine of 0 is 1. So I end up with a positive 3 plus a positive 3 gives me 6. Alright, our next one is from negative 3 to 4, 8 minus 3x dx. Now 8 minus 3x is just a linear function. It's continuous everywhere. So there is no problem with getting an antiderivative and having a continuous function here. So we can do 8x as the antiderivative of our first term, minus 3 times the antiderivative of x will be 1/2 x squared. We're going to evaluate from negative 3 to 4. Again, I want to simplify this just a little bit. I'm going to write it as 8x minus 3/2 x squared, and we're evaluating from negative 3 to 4. Put 4 in first. 4 times 8 is 32, minus 4 squared is 16. 3/2 times 16. 2 will cancel with 16, leaving an 8, times this 3 is a 24. So putting in the 4, I get 32 minus 24. Then we're going to subtract. Putting in negative 3. Negative 3 times 8 is negative 24. And if I put negative 3 here, negative 3 squared is a positive 9, times 3 makes 27 halves. Okay, well 32 minus 24 gives me 8. This is going to change to a plus 24 and a plus 27 halves, isn't it? Okay, well I'm going to go ahead and add 8 and 24, and that's going to give me 32 plus 27 halves. I think I'm just going to put 32 over 1, get a common denominator. I would have 64 halves plus 27 halves. I believe that's 91 halves then. Some of this arithmetic actually is harder sometimes than finding the antiderivative. Of course, if you have one of the calculators that does fractions, you can do that. I would always recommend that you leave your answer in fraction form. It's okay to go to decimals as long as they are exact, but keep in mind with like thirds, you can't write down an exact decimal for that, so I might suggest on those that you not go to the decimal form. Alright, well let's take a look at this one. We are to find the definite integral from 0 to 1 of x times the square root of 1 minus x squared with respect to x. Now this problem will be a little bit more difficult than the ones we've looked at simply because we're going to have to do a u substitution in order to find an antiderivative. I'm going to rewrite this just slightly. 0 to 1, x times the quantity 1 minus x squared to the 1/2 power times dx. So our logical choice for u would be to let it be 1 minus x squared. Then du would be minus 2x dx. Since I have an x dx up here, I'm going to solve for x dx here. Negative 1/2 du will equal x times dx. Now we're going to start the substitution process. Okay? Now I'm not going to put numbers on there just yet, and I'll explain why. This part right here will be u to the 1/2. And the x dx can be replaced with negative 1/2 du. So I'll put that in. Now let's talk just a second. Recall that this symbol is implying that we are doing things with respect to x. That means these numbers are x's. Everything here is with respect to x. So this would be an x value of 0 and an x value of 1. When we do a substitution, we are now doing things with respect to u. It would be incorrect for me to put a 0 and a 1 here because 0 and 1 are x's, they are not u's. But it's a real simple matter to convert. Remember, this is what we're using to convert between x's and u's. So all we have to do is use this formula. If x is a 0, putting it here, u would equal 1 minus 0 or 1. So whenever x is 0, u is 1. Notice the lower limit of integration. Now for my upper limit of integration, x is 1. So u would equal, going back to this formula, 1 minus 1 squared, or 1 minus 1, which is a 0. Okay? Now I want you to be sure you understand, so you know that I didn't just flip these, but I actually used this formula to convert not only everything here in terms of u, but also my numbers. Now, let's find an antiderivative. I can bring the constant negative 1/2 down. The antiderivative of u to the 1/2, if I add 1 to that exponent, I have 3/2, which places 2/3 in front. And I'm going to evaluate from 1 to 0, my new limits of integration. Let's simplify this just a little bit. Our 2's would cancel. I would have negative 1/3 u, and I'm going to remind you again, that means the square root of u to the 3rd power. Now, here's the good news. On indefinite integrals, when you did a u substitution, after you got to this point, you had to substitute x back in. You do not have to do that with your definite integrals because you have already converted your numbers from x's to u's. So these numbers are values of u, so they can go directly into this form right here. So putting our upper number in first, I have negative 1/3 times the square root of 0 cubed. Then we're going to subtract. We'll put in our lower limit, so negative 1/3 times the square root of 1 cubed. Of course, 0 cubed is 0, or the square root of 0 is 0, and that cubed is 0, so we get a 0 here. This will change to a plus 1/3. The square root of 1 is 1. 1 cubed is 1, so I just get 1/3 as my solution. So I'm reminding you here that when you change variables in definite integrals, limits of integration must be in terms of the same variable that you are finding the antiderivative with respect to. So when you do a u substitution, not only do you convert the integrand, but you also convert those limits of integration, those numerical values. But then you can just substitute straight into your antiderivative in terms of u. Well, let's look at another one. We have the integral from 0 to pi, 3 times cosine squared x sine x dx. Again, we're going to require a u substitution. Notice the cosine is to a power. So I'm going to let u equal the cosine of x. The derivative of u, du, then, would be negative sine x dx. You'll notice right here you have sine x dx. So let's multiply by negative 1 on both sides and solve for sine x dx down here. So we'll have what we can replace. All right, we're going to start converting. Now, the 3 is a constant, so I can just bring that 3 down. In place of cosine, I'm putting u, so I will have u squared. In place of sine x dx, I can place negative du. Now, remember, you're multiplying by that. Now, let's convert these numbers. And this is the formula that we use. So whenever x is 0, u will equal the cosine of 0, which is 1. So my lower limit is 1. If x is pi, u equals the cosine of pi, using this formula again. The cosine of pi is negative 1. So my upper limit is negative 1. Okay? Now, this negative 1 times 3 is a constant we can bring down. U will go up to the 3rd power, putting 1/3 in front. We're evaluating from 1 to negative 1. Let's simplify. That will be a negative 1 times u cubed from 1 to negative 1. All right, let's place the upper number in first. So I have minus here. If I put a negative 1 in here, negative 1 cubed is a negative 1. Subtract our minus, and if I put a 1 in, 1 cubed is 1. So this changes to a plus 1, and of course that changes to plus 1, so my value is 2. Evaluate the definite integral from 0 to pi over 8, secant squared 2x dx. Again, we're going to need to do a u substitution. Now, I do know the antiderivative of a secant squared is a tangent, but the problem here is the argument is not just an x. So my u substitution will let u equal 2x. du then is 2 times dx, which means that dx is 1/2 times du. So Making our substitution, I will have secant squared u, and in place of dx, I have 1/2 du. Now again, remember, we need to convert our numbers. U is equal to 2 times x. So if x is a 0, u equals 2 times 0, which is 0. Okay? And if x is pi over 8, u equals 2 times pi over 8, which is pi over 4. Okay? Now, we're going to find our antiderivative. I can bring the constant 1/2 down. The antiderivative of secant u with respect to u is the tangent of u. We're evaluating from 0 to pi over 4. Now remember, these are values of u. They go straight in for u. So putting my upper limit in, I have 1/2 times the tangent of pi over 4. Then subtract. Putting in the lower limit, I have 1/2 times the tangent of 0. Now the tangent of 0 is 0, so that term's going to drop out. Do you recall what the tangent of pi over 4 is? The tangent of pi over 4 is 1. Remember, pi over 4 is like your 45 degree, and your 45 triangle looks like that. The tangent is 1 over 1. So the value of my definite integral is just going to be 1/2. This next problem presents an interesting situation. We're trying to find the definite integral. This is not a parenthesis. These are absolute value signs. We want the definite integral from 0 to 4 of the absolute value of x squared minus 4x plus 3 with respect to x. As it turns out, the absolute value does create some problems for us. We cannot just ignore those. So, in preparing us on how to get rid of those absolute values, let's talk about absolute value for a second. If you find the absolute value of 3, that's just 3, isn't it? What's the absolute value of negative 3? Well, that's also 3. But let's talk about the implications here. If what is inside my absolute value is positive, then I can just drop the absolute value signs off and I have the correct solution. However, if what is inside my absolute value is negative, I need to change the sign, don't I? So let's look at it like this. If I have a negative inside here, I can take the opposite of that negative, and that gives me my solution. So if what's inside is positive, we drop off the absolutes. But if what's inside is negative, we change its sign by multiplying by a negative. We're going to need to remember that to remove these absolute values. You see, x squared minus 4x plus 3 will sometimes be positive and sometimes be negative depending upon the value of x. In fact, if you look at this, if x is a 0, we have a positive value. But notice if x is 4, what happens? 16 minus 16, well that's 0 plus 3, that still looks positive. Well, look in the middle of the integral. What if x is 2? 2 squared is 4, minus 8 would be a negative 4, plus 3 is a negative number. So somewhere in the middle of this interval, this becomes negative for a while. So we're going to need to figure out where is this value positive and where is it negative. It may have been a while since you've done that, so I want to remind you how to do that. We're going to look at x squared minus 4x plus 3, and we're going to analyze its sign. So what I'm going to do first is factor. That would factor into x minus 3 times x minus 1, wouldn't it? Values of x equal 3 or x equal 1 would make this quantity become 0. So what I'm going to do is locate on the number line the values 1 and 3. Okay? X equal 1, x equal 3 would make this quantity equal 0. It can only change signs in between those places where it becomes 0, if you recall from algebra. So all you have to do once you have found these places is if you pick a number to the left of 1, like for instance 0, and you substitute it in for x, you can either do it here or you can do it here. Notice that if you put a 0 in here and here, you have a negative 3 times a negative 1, which gives me a positive answer. So to the left of 1, x squared minus 4x plus 3 is always positive. Now notice between 1 and 3 we can use the number 2. We've already shown you earlier, but notice here 2 minus 3 is negative, 2 minus 1 is positive. A negative times a positive is negative. In between 1 and 3, that polynomial is negative. And then once we get past 3, if we choose a number over here like 4, 4 would make both of those factors positive. Now, you'll notice 0 to 4, 0 would start here, 4 would end here. So between 0 and 1 we're positive, between 1 and 3 we're negative, and between 3 and 4 we're positive. So what I need to do is break this integral up into 3 separate integrals. The first one I'm going to go from 0 to 1. In that interval, this is positive, so I can just drop the absolute value signs and replace them with parentheses. Okay? Now, from there, I'm going to pick up at 1, and I'm going to go to 3. Now, in this interval, this is negative. So to get rid of the absolute values, I need to change the sign, multiply it by negative 1. So that would make that negative x squared plus 4x and minus 3. Okay? And then I'll have a third part I'm going to write down here. Picking up at 3, then I'm going to continue until I get up to 4, and in that interval I'm positive again, so I can just drop off my absolute values and replace them with parentheses. It's very important that you understand the difference. The parentheses are just there to kind of group and say this whole thing is with respect to x, whereas the absolute value is telling you to be careful about the sign of your answer. Now, we're going to evaluate these integrals separately. So we'll find an antiderivative here first. That would be 1/3 x cubed. And I'm just going to go ahead and simplify that. That would be minus 2x squared. Do you see that? The derivative of minus 2x squared is negative 4x plus 3x. This part is going to be evaluated from 0 to 1. Okay? Now, plus, we're going to find an antiderivative here. Well, that one is going to be negative 1/3 x cubed plus 2x squared minus 3x. That one is to be evaluated from 1 to 3. Notice once I found this antiderivative, this will be basically the same except opposite signs. And then finally, on the last one, we're back to positive value first, 1/3 x cubed minus 2x squared plus 3x, and this last one is evaluated from 3 to 4. Okay, let's put in our limits. So the upper limit goes in first. So putting in a 1, I have 1/3 minus 2 plus 3. Subtract. If I put a 0 in, notice every term is 0, so I'm just going to put minus 0 there to remind me I've done that lower limit. It's just all zeros. Okay, plus. Now we're putting a 3, my upper limit, in here. 3 cubed is 27. 1/3 of 27 would give you a negative 9 right there. 3 squared is 9 times 2 is 18, so plus 18. And then finally minus 9, putting in the 3. Then subtract. We're going to put the lower limit in. I have negative 1/3 plus 2 minus 3. Okay? Now, we're to the last one. We're going to put the 4 in first. 4 cubed is 64, so I have 64 thirds minus 4 squared is 16 times 2 is a negative 32 plus 3 times 4 is 12. Then remember we're going to subtract. We put in our lower limit. 3 cubed is 27. 1/3 of 27 is 9. 3 squared is 9 times 2 makes a minus 18, and 3 times 3 is a 9. Okay? Now we just need to do a bunch of arithmetic here. Negative 2 plus 3 gives me a 1. I'm just going to leave the fraction. I have 1/3 plus 1. Okay? I can ignore this part. Negative 9 minus 9 is negative 18 plus 18. All that adds to 0. Okay? Now remember, this negative will distribute, so I'll have a plus 1/3. And 2 minus 3 is a negative 1, but this negative distributing would make that a plus 1. Plus 64 thirds, I'm going to bring that down. Negative 32 plus 12 is a negative 20, isn't it? And then finally, 9 plus 9 is 18 minus 18, that's a 0. So we can get rid of that. Okay, well, let's see what we have. I have 1 plus 1 is 2, minus 20 is a negative 18. 1/3 plus 1/3 is 2/3, plus 64 thirds makes a plus 66 thirds. Now, 3 will divide into 66, won't it? 22. So negative 18 plus 22 is going to give us a positive, what, 4 as a solution? All right, I wanted to look at this definite integral because the u substitution can be a little bit tricky if you're not careful. I'm going to rewrite this one as the integral from 3 to 7 x times the quantity x minus 3 to the 1/2 power times dx. Now, since I have this quantity to a power, I'm going to let u equal x minus 3. That means du is going to be 1 times dx. So notice I can replace that, but I do not have a replacement for x yet, okay? What we're going to do is take this formula right here and solve it for x. So if I add 3, u plus 3 will equal x. So in replacing things in my integral, the x is u plus 3. This is u to the 1/2. And dx is just du. Okay? Now let's change our numbers. Remember, if x is 3, u would equal 3 minus 3, which is a 0 for the lower limit. And if x is 7, u would be 7 minus 3, or 4 for the upper limit. Okay? Now, we're not quite ready to find an antiderivative. I need to multiply this out. So u times u to the 1/2 is u to the 3/2 plus 3u to the 1/2. I just distributed there to multiply that out. Now I'm ready for the antiderivative. So here u will go up if I add 1 to 5/2, which places 2/5 in front. I'll bring down my 3. U would go up to 3/2, which places a 2/3 in front. And we're to evaluate that from 0 to 4. All right, I'm going to rewrite it just a little bit. 2/5. Remember, this means the square root of u to the 5th power. Of course, my 3's here cancel, so I have a 2. This one means I have the square root of u cubed. All right, remember these are u, so let's put them in. So I have 2/5. If I put a 4 here, the square root of 4 is 2. 2 to the 5th is 32. Okay? Plus 2. Putting in the 4 here. Square root of 4 is 2. 2 cubed is 8. Subtract. The lower limit is a 0. So the square root of 0 would be 0. The square root of 0 would be 0. All of this would be 0. All right, well, let's see what we have here. 2 times 32 is 64 fifths, and 2 times 8 is 16. That's over 1, so let's get a common denominator. I have 64 fifths, getting a common denominator of 5. That's 80 fifths, so I have 144 fifths as my solution. I hope at this point that you're beginning to get the idea of what the fundamental theorem of calculus allows you to do. Find an antiderivative. Sometimes that requires a u substitution, but find your antiderivative. Evaluate your antiderivative at the upper limit of integration first, subtract, evaluate at the lower limit of integration. Remember, if you use a u substitution, you also have to convert those numerical limits of integration over to values of u also. And don't forget, because we get so involved with doing these antiderivatives that we forget to look, is our integrand continuous over that interval where our limits of integration are showing. Now, recall that when we looked at the definite integral using the limit of a sum, we talked about the fact that that can give you area under a curve. So I'm going to do an area problem for you using the fundamental theorem of calculus. We want to find the area bounded by the graph of y equal 3x minus x squared, the x-axis, and the vertical lines at x equal 1 and x equal 4. Now, I'm only interested in what goes on between x equal 1 and x equal 4, so we're going to graph this equation between those two x values. Notice if x is a 1, I have 3 minus 1 is a 2. So whenever x is 1, y is 2. Okay? If x is a 2, I'm just going to go through a couple of values here. If x is 2, I have 6 minus 4. 6 minus 4 is a 2, so that's also a 2, isn't it? Okay, if x is a 3, 9 minus 9 is a 0. And if x is 4, I have 12 minus 16 is a negative 4. Obviously, this is a parabola, so we are not finding the vertex at this point, but it'll go up like this, come down like so. Now, at x equal 1, I would have this vertical line. Here's my x-axis, so we're talking about this area right here. The vertical line at x equal 4, and your x-axis, we also want this area. I want you to notice part of the area is above the x-axis and part of the area is below. To get the area above the x-axis, we will go from an x value of 1 to an x value of 3. So we're going to integrate from 1 to 3. We'll place our function 3x minus x squared there. So the definite integral from 1 to 3 of 3x minus x squared is going to give us that area under there. Now, since this area is below the x-axis, plus, from 3 to 4, our graph went below the x-axis, so recall there you have to make your function negative. You're basically saying 0 minus that. So making that negative, we get negative 3x plus x squared. That way we'll get a positive area. If I integrate straight from 1 to 4, I get the net difference between the positive area and the negative area, because this would stay negative. By splitting this up and changing the sign on my integrand for this part, I'm changing this into a positive area, so I'm getting the total area. Alright, let's find our antiderivatives. I will have 3 halves x squared. Do you see where I'm getting that? That would be 1 half x squared times 3 minus 1/3 x cubed. We're evaluating this one from 1 to 3. For the second one, we would have minus 3 halves x squared plus 1/3 x cubed. And that one we're evaluating from 3 to 4. Alright, we're going to put in our 3. We get 9. 9 times 3 is 27 halves. Minus, putting in the 3 here, I get 27. 1/3 of 27 is a 9. Subtract, put in our lower limit. Putting in a 1, I get 3 halves minus 1/3. Okay? Now over here we're going to put the upper limit in. So 4 squared is 16. 2 will go into 16 8 times, so that'll be a negative 24. And then 4 cubed is 64, so I have plus 64 thirds. Then we'll subtract, putting in our lower limit. 3 squared is 9, times 3 makes negative 27 halves, plus 3 cubed is 27, 1/3 of 27 is 9. Okay? Now again, I'm going to kind of remove some parentheses here, but I'm going to leave some of these fractions till we can combine some of them. I have 27 halves minus 9. Notice here, if we distribute our negative, I have minus 3 halves plus 1/3. I have a minus 24 plus 64 thirds, and this negative distributing makes a plus 27 halves and a minus 9. Now let's look at our halves, which is these three. Okay, 27 plus 27 makes 54. 54 halves minus 3 halves makes 51 halves, doesn't it? On my thirds, I have 1/3 plus 64 thirds makes a plus 65 thirds. And then on my numbers, I have a -9. A -9 is a -18 and a -24. Let me look at that right there. I'm trying to do that in my head and having trouble thinking. So that's a -42 minus 42. Let's put that over 1. Let's get a common denominator, which is 6. So multiplying this one by 3, I have 153/6. Multiplying this one by 2, that's 130. And then multiplying this one by 6, that's 252, minus 252. So I have 153 plus 130 minus 252 gives me 31/6 for my area. So just remember with area, if you want the area bounded by the curves, you don't want net difference of positive and negative area. You need to split up your integral where part of your graph dips below the x-axis. There's another theorem which is referred to as the mean value theorem for integrals. The word mean basically says average. You may not have used that, but if you've studied statistics, you know that the mean is the same thing as the average. So we're talking about the average value theorem for integrals. If a function f is continuous on the interval from a to b, there exists a number c in the open interval ab, not at the endpoints, but somewhere in the middle of that interval, where the definite integral from a to b of f of x dx equals f of c times b minus a. Now, the theorem is usually written in this form and is usually proved in this form, but we usually rewrite it in a form that tells us how to find the average value of a function. If a function f is continuous on the interval from a to b, then the average value of f on this interval is given by 1 divided by b minus a times the integral from a to b of f of x dx. I want you to look back here just a second. You have the integral from a to b of f of x dx equals f of c times b minus a. Notice on this equation, if you divide both sides by b minus a, this would cancel out over here, leaving f of c, and you would have a 1 over b minus a here. That would look like this part of the formula here. So basically, they have taken that mean value theorem, solved it for f of c. They're saying f of c equals this, and that f of c turns out to be your average value of the function. This is really a pretty simple formula to remember. To get the average value of a function over a closed interval, you're going to integrate from a to b over that closed interval, your function. But in front of that, you're just going to have a coefficient 1 over the difference between your right-hand endpoint of your interval minus your left-hand endpoint. Let's calculate the average value of a function. Find the average value of the function over the given interval and find the point or points where the function assumes its average value. Well, let's look at this. To get the average value, I'm just going to abbreviate that. The average value would equal 1 over, remember our formula said b minus a? Well, b is a 1 and a is a 0, so that's 1 over 1 minus 0. Then you will integrate from a to b, 0 to 1. You'll put your function in, negative 3x squared minus 1, and you're integrating with respect to x. Well, let's work on this. Of course, 1 over 1 minus 1 is just a 1, so I can drop that off. Finding an antiderivative, I will have a negative x cubed. Notice the derivative of that is negative 3x squared minus x. So the antiderivative is negative x cubed minus x. We're evaluating from 0 to 1. putting 1 in first, I get negative 1 minus 1. Subtract. Putting in 0, everything here is going to be a 0, so that'll be gone. Minus 1 is a negative 2. Okay? So the average value of the function is negative 2. Now, it wants to know, where does this function assume its average value? In other words, when is this function value negative 2? So we would say negative 2 is equal negative 3x squared minus 1. And we're going to solve this for x. Well, let's see. I can add the 1 over here, which makes a negative 1 equals negative 3x squared. Dividing by negative 3, I have 1/3 is equal to x squared. Solving for x, I would have plus or minus the square root of 1/3. That would be plus or minus 1 over the square root of 3. If you rationalize, that's plus or minus the square root of 3 over 3. Now, you'll notice when I solve this equation, I got 2 values. But which of those values is between 0 and 1? Well, obviously, the negative square root 3 over 3 is not. So I will say at x equals positive square root 3 over 3, I will assume my average value of negative 2. Now, I just want you to be sure and understand, if you take the square root of 3 and divide by 3, that is approximately 0.58. And notice 0.58 is definitely in this interval between 0 and 1. We have one other concept that we want to talk about on this lesson: integration of even and odd functions. If f is integrable on the interval from negative a to a, that just means we can find the integral value. We can find an antiderivative and evaluate it. If a function is integrable on the interval negative a to a, notice that's like saying negative 2 to 2, negative 5 to 5. So these are opposites. If f is an even function, the integral from negative a to a of f of x dx can be found by doubling the interval from 0 to a of f of x dx. Recall that an even function basically is symmetric to the y-axis. And so what that's telling you is that the part of the graph to the right of the y-axis would look exactly like would be a mirror image of the part to the left. And so instead of having to integrate from the minus 3, say, to the positive 3, we can just go from 0 to 3, get that area, and then double it. If f is an odd function, the integral from negative a to a of f of x dx will always be 0. Recall that an odd function switches values. So on one side, if your graph is above the x-axis, on the other side it would be below, and so those areas would cancel out. So we're going to look at a couple of these examples and use this idea of even and odd functions. Evaluate the integral from negative 2 to 2, x squared minus 1 dx. Now, first of all, notice your limits of integration. These are opposites. This even and odd function thing only works when these limits of integration are opposites. So since these are opposites, I'm going to look at my function. I notice that if I change x to negative x squared would be just like x squared. And so this function would not look any different. That makes it an even function. Since it is even, I can just put a 2 and integrate from 0 to 2 x squared minus 1. Now, one reason that this is nice is because it's so much easier to evaluate things when you substitute in a 0 than it is for a negative 2, isn't it? All right, well, let's do this one. I'm going to bring down this 2. My antiderivative would be 1/3 x cubed minus x. And we can evaluate from 0 to 2. All right, putting in the 2, I have 2 cubed is 8, so I have 8/3 minus 2. Notice, subtract. If you put 0 in, you just get 0. That's the nice thing about the 0. All right, so we have here 2 times 8/3, and of course 2 is 6/3, isn't it? So I have 2 times 2/3, which gives me 4/3. Now, if you did not catch that this was an even function, if you just found the antiderivative 1/3 x cubed minus x, and you put in the 2, subtracted, put in the -2, you should get this same answer. It's just that this is a lot less work, and that's the nice thing about it. Now, on this second one, if you're not paying attention, though, you're going to do a lot of work. Look at this integrand. That is really a difficult integrand. You'd have to do a u substitution on both parts in order to get there. Notice again, though, your limits of integration are opposites, -pi/3 to +pi/3. So what we're going to do is we're going to investigate and check to see if this is an even or an odd function. The way you do that is like I did up here, you replace x with -x. If that doesn't change the function, it's even. If it makes the function have opposite signs, then it's odd. So we're going to look at this, and I'm going to put sine to the 5th -x, cosine -x, minus sine to the 3rd -x, cosine -x. Do you recall your negative angle identities? I might remind you, the cosine of -x is the same thing as the cosine of +x. But the sine of -x is the opposite.